maybe I didn't say it clearly enough, so let me say it clearly. At this point, we need to know what harmonic oscillator is. That's example of perfect regular behavior. And then we have to have its wild sister, the perfect chaotic behavior. Now, in between, the dragons live, so all the research it's called theory of phase transitions or something. All the research is in between. But we have to have a very clear idea what it means to be regular and what it means to be chaotic. And it turns out, when you think about it in this Bernoulli way, whenever you look at a neighborhood and linearize it, there are two kinds of solutions. They're either complex number solutions, of which harmonic oscillator is, where you have pure complex unit length numbers. So you're only getting phase. That's the oscillatory solution. Or you have hyperbolic solution where you go in and out, what's called a saddle. So Bernoulli is the same as harmonic oscillator, that I explain in a longer version of this. And it's just, harmonic oscillator is described by Hooke. It says, I push something and it pushes back. That's Hooke principle. And if energy is conserved, this gives you a harmonic oscillator. And there, Hooke has a wild sister. I call her a cat. The cat is such that you push it, it goes away. So, it has a positive, negative elasticity. You try to get it to do something, it just goes away. Now, because we're in the same room with the frigging cat, a cat goes away, but it has to come back because there is no place to go. So it turns out, that's called entropy, positive entropy. So all cats are running away, but they're all coming back all the time because, what can they do? I mean, they're in the same room with it. So they pretend not to listen to us, and they certainly don't want to push back. They push away. But so they have positive Lyapunov because they don't oscillate, they're hyperbolic. But you have to count the number of waves coming back, and that's what Bernoulli map was an example of. Every little sub-interval there was a cat. You pushed it, it ran away because all the slopes are positive. But then it comes back in many possible ways, and that you can count in this simple example. So that's the essence of it. There are two things that can happen: either pure order, which is oscillation, or pure disorder. But when they get coupled in some nonlinear way, there is an immense range of things that happen in between. So, for example, you start the Ising models, there is some phase transition between everybody being frozen and everybody being like cats, chaotic. And there's an interesting theory of that. But in dynamical systems, there are very many complicated ways, which you just described. You can be chaotic, you can get close to regular behavior. So it looks to you've gotten glued to oscillator. And you go around, follow this, and that's very boring. Just that's very simple. There's no exponential there for a while. But then you find a little path outside because there is an unstable direction that you finally reach. And then you burst exponentially away and you do all kinds of wild stuff around and you end up stuck someplace else. So those are mixed state spaces that exhibit both kinds of behavior, local stability and local instability. And, that's where all the research is. So transition to turbulence is complicated. Melting of a material is complicated because it turns out that's the regime where, large chunks look frozen or there are long periods. And, in state space, there is a border of order. There are places when you get to the border of order, you don't know what to do. So you just hang there forever. But if you're on either side of it, on one side you oscillate, on the other side you go bananas, you know. So that's where all the research has to be done, because individual systems have different ways of going through phase transitions, meaning phase being different kinds of behaviors. In this case, chaotic versus orderly, but you know, in statistical mechanics or field theory, there are other ways of saying that.
Okay. Yeah. No, thanks. That makes a lot of sense.
So you know, I'm just trying to teach you a pure example you can explain to anybody. Flipping coin. You know, you cannot possibly get in a sequence where you guarantee that every 17 times you get the same sequence of heads and tails. You know it intuitively that cannot happen, right?
Mm-hmm.
If you throw a dice, you know, have 6 outcomes. That was what that example of Bernoulli map was, 6 possible outcomes. Now, if you cheat, you know, the dice maybe can get caught in some finite sequence, but if you have an unloaded fair dice, it cannot. So this is the pure example and the simplest example. And the reason why we have to wait so long is because we have intuition about flows, but we don't have intuition about maps. So you might wonder, why the hell am I teaching you maps if I started with maps? In math course, you just start with maps because who cares about intuition? You know, you just have to prove stuff. But here, we don't have that luxury. Okay, I'm running away.
Yeah, thank you.